The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so I'm going to work through problem number 3 in the Physics 2020 Midterm Exam 1. And in this particular problem, it asks us, it says that a diver running at 5 meters per second dives out horizontally from the edge of a platform that is 3 meters from the water. How long does it take the diver to hit the water? Okay, so we are going to be working through this problem, and in order to do so, I encourage you to have your formula / review sheet for the midterm exam 1 given in the class. It might be helpful for you to have this review sheet in order to follow along. I'm going to be pulling formulas from this review sheet in order to solve the problem. Okay, so given the information in this problem, we can, sometimes it's helpful for us to draw a diagram in order to give us a better visualization of what's actually happening. This is kind of useful in physics sometimes if you're able to do that. And so I'll just draw a quick diagram. Let's see. And so we've got basically our platform here with the person standing on it, and they're going to be diving out horizontally at 5.0 meters per second, and you have basically the water below, okay, and we know that the distance between the water and the platform in the y direction. And so over here we can set up our coordinate system where this is the positive x direction and this is the positive y direction. And in physics you need to basically define what your coordinate system is going to be, and it needs to be consistent throughout the problem. And so if we define the positive y to be this way, everything that we do in terms of the problem needs to follow the same coordinate system that you have defined here. And so if we define the positive y, that means then, and this would be positive x, that means that this is the point, this is the origin, which is the point 0. Okay? And so we also are given some information that the initial velocity diving out from the platform horizontally, so that we know that VO is equal to 5.0 meters per second, because VO is the initial velocity. But we also know that it specifies that he dives out horizontally. Okay, so that implies, so horizontally implies there's no VOY. There's no initial velocity in the y direction, only in the horizontal direction. Okay? And that also tells us that the platform is 3 meters from the water, so that this is basically the distance between the water and the platform is 3 meters. And it asks us to find how long does it take the diver to hit the water. So what we're actually doing, we're trying to find, so we want to find delta t, and if we define delta t as the final time minus the initial time, and we know that the initial time is 0, then we can call the final time TF, or just T. Okay? So So we want to find t. All right, and we can look on our formula sheet to see if we can find a formula to help us solve this problem, given the information. And when reading the problem, we know that we're dealing with projectile motion. This is a object that is moving in either the x or y direction, or both, with nothing else acting on it except for gravity if we neglect air resistance. So that's basically the definition of projectile motion. And so on the second sheet of the formula, sheet, we have basically different equations that we can use for projectile motion. And if we look at the equations in the y direction, we see that there's an equation that has y is equal to y sub 0 plus v sub 0 sine theta sub 0 t minus 1/2 g t squared. And actually, this is the equation that we want to use. So this is our equation that we want to use from the projectile motion set of equations. And the reason why we want to use this equation, because if we look through it, we know the initial velocity, okay? So that's important. The equation has to have the initial velocity in it. We also want to find the time, and so we have the time is in this equation, which is important because if we're trying to solve for time, t has to be there. And we know y, okay, and we know the initial y. All right, and so if we define so if we basically solve this equation, we also know theta, the initial theta. Theta is basically, in a projectile motion, is from wherever you're launching from, it's the angle that it makes from your launching point with a line that's straight across. So basically, if this guy is going to be diving out, okay, if he was diving with some initial, let's say, y value, then this angle that he makes with the horizontal, what we call theta. But since he's actually not diving out with any y component, he's actually diving out just horizontally, there is no y component. That means our theta then is equal to 0. Okay, so our theta is equal to 0. All right, and so we can, if we know that theta is equal to 0, then basically this whole term, sine of 0, is equal to 0. So this whole term goes to 0. Okay. So now, if we can solve this equation for t now, and so if we do that, we'll get y minus y sub 0 is equal to minus 1/2 g t squared. Okay, and then basically solving this for t, we get t is equal to plus or minus the square root of 2 times delta y divided by g, and that will be negative. The 2 will be negative. All right, and that's basically just simply solving this equation for t. And when we do that, since we have a t squared, we're going to have to take the square root. When you take the square root, you're going to get plus or minus. But since we're solving for time, there's no such thing as negative time, so we don't worry about the negative answer for the time. Now, we also see under the square root, we'll have a negative 2. And we know that we can't take the square root of a negative number, so that means that this whole term under the square root has to be positive somehow. And you see, well, how can it be positive? Well, if we look at delta y delta y is defined as your initial, or your final, so it's going to be y minus your initial. Okay? And so, if we know that using our coordinate system, our final y, okay, if the diver starts at a height of 3 meters, we know that's the initial y. Okay, so he starts at a height of 3 meters, and then our final y is where he ends up. Well, he ends up at the water, but the way our coordinate system is set up, that's actually at 0. So our delta y is actually a minus 3. Okay, and so whenever we substitute this information into the this equation for t, we'll see that we'll get a positive number under here now. Okay, so let's do that. Let's create some room here. So we've got t is equal to the square root of negative 2 times delta y over gravity. Okay? So we know that t is equal to the square root of minus 2. Alright? And delta y is minus 3 meters. And we know that g is 9.8 meters per second squared. Alright? And just under the square root, we'll see that the meters cancel out, and we have a second squared in the denominator, but when we divide it out, it becomes in the numerator. And since we're taking the square root, this square term will go away, so we'll just have a seconds to the first power. And when we work this out, we get 0.78 seconds. Okay? And basically, that is the answer for this problem.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.